This video is on the common ion effect, and you'll see that by the end, I'll try to relate it to Le Chatelier's principle. It's really just a application of Le Chatelier's principle, and so Le Chatelier, if you remember, is trying to predict which way a reaction will shift if you have both reactants and products present at the same time. So let's start our tutorial. So first of all, here's the key. I'll be using some of these terms when we cover buffers and this video also. So strong acid is SA, a strong base is SB, weak acid WA, and a weak base is WB. You'll see that I may use these terms. So a weak acid, by the way, is like HF or HNO2, etc. A weak base, these are usually amines. So like NH3 or CH3, NH2, etc. So, and then a strong base, of course, is like something with hydroxide, and then or a group one with hydroxide, or the heavier group twos, and then strong acids, the seven strong acids. But also a weak acid is also could be a charged amine also. So don't forget about those. So it might be a charged amine like NH4 plus 1 or CH3 NH3 plus, okay, something like that. And a weak base, it could be an amine or it could be the conjugate. So remember that I was calling these conjugate acids of weak bases. Or when you have a weak base, it could be an amine or it could be the conjugate of a weak acid like that or like that, etc. So, and then I was calling these conjugate bases of weak acids. Okay, so WB and WA can mean lots of different things, and hopefully you have enough background where we can recognize them readily. So let's move on. So the common ion effect is something that will happen when both a weak acid or a weak base are present with their conjugates. So, and I wrote A minus or B plus in the same solution. So an examples out of the stuff I wrote is, let's say you have HF and you have like NaF. Okay, remember that this doesn't do anything if you had NaF, so that essentially you have HF and F minus. Okay, that's an example of the common ion effect would happen if you had those two in significant amounts. Um, you would also get, like, for example, if you had a weak base like NH3 and you had its conjugate NH4 plus. Now, when you read these problems in textbooks, they're not going to write NH4 plus. They're going to show it in a salt form like that. But you just have to recognize that this is the same thing as this because the Cl minus doesn't do anything. It's a spectator. Okay, so you would have NH3 and NH4 plus. So if you have those two in significant amounts, you would observe what's called the common ion effect. So if you do have weak acid or weak base and their conjugates, then you're going to see when you do an ice table, you'll see that there's not zeros on the product side. You'll see that there's something there on the product side. And so you'll see that the equilibrium will not shift to the right as much. So let's go ahead and do work an example because I think the numbers here will actually help explain the concepts more. So let's do two examples. One where this is should look familiar. You've done problems like this before. And then in the next example, we'll do one where the common ion will be involved. So example one is we'll do this problem. So calculate the pH of a 0.30 molar solution of acetic acid. Okay, and the Ka for acetic acid is 1.8 times 10 to the negative fifth. Okay, so you write your equilibrium. It's an acid, so we don't need to show water. So we show the proton dissociating. Set up our ice table. So all this is these are zeros here. So this will be, and This we know it'll shift to the right. Okay, so this go up by x, goes up by x. Okay, we solve our problem here, so we'll have x squared over 0.30 minus x equals 1.8 times 10 to the negative fifth. Using the assumption rule, we could assume that this is nothing compared to the 0.3. So x, if we solve this problem out, would equal the amount of H plus and the amount of acetate ion at equilibrium. This would be 2.3 times 10 to the negative third molar. Now what we'll do is we'll do the same problem, but we're gonna add the salt form of this. So we're gonna add the conjugate of this acid. So calculate the pH of a 0.30 molar solution of CH3 acetic acid and its salt, its conjugate. So and 0.2 molar NaCH3 sodium acetate. So this time, if we work this problem out, we'll see a notable difference on our ice table. So when we write the ion here, so this is the whole point of this whole slide is there's something here now. So this right here is this. Okay, and again the you need to recognize that this doesn't do anything. You have this you have a salt here, so you have the conjugate of this. Okay, so this is not going to be in the previous problem. This was a 0. You'll see here that it's not going to be 0. There's something there, and let's see what happens when there's something there. So if we solve this problem out, so this is still 0, and this we're going to put this number here, so 0.20. Okay, it's still going to shift to the right because this number is a 0, so there still needs to be some product created. Because if you look at Q, Q will still be less than K, so it needs to shift to the right because we need some number here. So this will go up by X, this goes up by X. Okay, and we'll get X times 0.20 plus X over 0.30 minus X, 1.8 times 10 to the negative fifth. Assumptions are going to be valid here. This is small enough to where you could assume that these are nothing. So compared to relative to the numbers they're being added and subtracted from. So this would just be x times 0.20 over 0.30. Okay, so this time our proton concentration, if we solve this problem here, then we'll get 2.7 times 10 to the negative fifth molar. So let's take a look and see what happened here. On this problem, there's nothing here and nothing here. So in this case, the reaction needs to shift to the right more than it does here. So if we apply Le Chatelier's principle on this one, let's draw a line here. And on this first problem, Q is much less than K. So therefore, the reaction, let's use a different color to emphasize this point. So on this reaction, Q was way less than K because there you have two zeros here. So this needs to shift to the right much more than if something is there already. Something is there already. Okay, now if we look at this reaction, there's something here. So it's preventing this. It doesn't need Q is just a little less than I mean, it's still less than K, so it needs to shift to the right. So we need to add numbers here. However, it doesn't need to go as much as this one because there's zeros there. So it doesn't need to increase its value as much as the first example because something is there already. And you could see that by calculating the amount of protons that are generated by the acid, here we only have 2.3 to the negative third, and here is two more decimals away from this one just because something is there already. So we could summarize that by saying that Q, so over here, Q is less than K, but not as much as if there there's something there. And when I say there's something there, I'm talking about the common ion effect. There is something there, and it's not zero. That's the common ion effect. So it resists change. The analogy, if there's something there, an analogy I'm thinking of, it kind of makes me think of is if you have a, this is kind of like a speeding car, like on the freeway. So I, as you can see, I can't draw at all. So this is like a speeding car. Okay, it's going super fast here. Now, if there's something there like this, then you have like a cop. There's like a police car here. Okay, and sorry about my drawing. So there's a police car and the siren is going off. It's saying stop speeding or slow down. Okay, so this car that was over here. Okay, it can't. It's just going the regular speed limit. So when over here when it sees there's no cop, then it goes. It's like full speed ahead. It's going 90 miles an hour. Okay, and then here it needs to go down back to the normal speed limit. Okay, because there's something here. So when there's something there, it kind of puts up like a stop sign saying, "Hey, wait, slow down over there on the reactant side. Just slow down. Okay, you don't need to go that fast." Okay, so when I say fast, this is different than kinetics. Kinetics is like it's totally different. So I don't want to. It's kind of where I guess where the analogy doesn't really work, but it's just saying you can't go here as much, come over here as much. Okay, so that's the common ion effect, and we'll see in the next video that this is what a buffer does, and it resists when there's two things there. They'll interact with like this guy is a base and this guy is an acid. So if you add an acid or base to this solution, it'll consume the acid or base that's added, and it will actually resist pH change. But it's an buffers are an application of the common ion effect. Um, we'll see in electrochemistry something called the Nernst equation is an application of the common ion effect. So there are many applications of this concept on the next topics that we cover all the way until the end of the year. Okay, so that's the end of our tutorial.